Good evening. My name is A Karunasingha. I'm a student from the Electronic and Telecommunications Engineering stream in Tech 34 of Kottala Defense University. My presentation today will be on generative adversarial networks, also known as GANs. So, to give a small introduction about GANs and their history. So, GANs are a fairly new concept. It was introduced in the year 2014 at the International Conference on Neural Information Processing Systems by a group led by Ian Goodfellow of the University of Montreal. So this is it's basically a technique that's used in semi-supervised as well as unsupervised learning. And the basic concept of GANs is based in game theory, basically on a minimax two-player game between two competing networks. So I will next explain what this minimax two-player game is. So a minimax two-player game, also called a two-person zero-sum game, is basically a game where a person can win only if the other person loses. Basically, there are two persons or two parties. A can only win if B loses, and B can only win if A loses. And in this situation, there is no cooperation possible. There is no situation where both A and B wins or both A and B loses. Either A wins or either B wins. There is no cooperation whatsoever. So in the context of GANs, who are the two parties or the two persons? The two persons are basically two networks. One network is called the generator, and the other is called the discriminator. So these are two networks that compete with each other in this two-person zero-sum game. So the generator, what basically the generator does is it generates believable fake data, and its objective is to maximize the probability of the discriminator making a mistake. And if you look at the discriminator's job is to distinguish between fake data created by the generator as well as real data. The objective of the discriminator is to minimize the probability of the generator fooling the discriminator. So we can see that how this is a zero-sum game. Basically, if the discriminator is able to identify between fake data that is created by the generator and real data, then the generator loses, the discriminator wins. And if the generator successfully fools the discriminator into thinking that the data created by it is no different to real data, then the generator wins, the discriminator loses. So there is no situation where both these parties or both these networks win. So one must defeat the other in every case. So just to give an overview of a typical GAN system, so we see there are two inputs. One is so in this case we think of images, a set of real world data that is provided as samples, as well as random input that is provided to the generator. So what the generator does is it creates sample data based on that random input. So the initial data that it creates can be completely random based on the random noise that is input into the generator. And so then for the discriminator, the inputs are the samples taken from the real image set as well as the sample of fake data sets that's taken from the generator. And then what the discriminator does is it tries to distinguish between these two, and it calculates two outputs called the discriminator loss and generator loss. So we'll see how these values affect the training of the GAN or the generative adversarial network. So if we take in GAN training, so like I said before, the generator first takes in random noise as input and outputs data. So initially the data that's output by the generator is obviously very fake. You can tell easily you can easily distinguish between generated data as well as real data. So in this situation, what the discriminator does is it takes the fake data generated by the generator and it basically sees how different are these two are the generated data from the real data, and it calculates something called the generator loss. So this is important in the next step. The next step, so we know the generator loss. So this generator loss is back propagated to the generator once again from the discriminator, and the generator uses this generator loss to adjust its weights, so that it can create more accurate data. So with each iteration, so in each cycle this happens, the generator starts creating more and more realistic data, which is more and more harder to distinguish between real and fake data. And then when it comes to a situation where the discriminator can't, where there is certain data points that the discriminator can't distinguish between the generator, the generator data as well as the real data, then it calculates something called the discriminator loss. And based on that discriminator loss, the discriminator adjusts its weights. So basically what's happening here is, using the generator loss that's calculated, basically the generator adjusts its weights so that it can create more realistic data, and then in each cycle, based on the discriminator loss that was calculated, the discriminator adjusts its weights so I can better distinguish between fake data generated by the generator as well as real world data. So this process continues, and it comes to a point where the discriminator finds it extremely difficult to distinguish between real data as well as generated data. So the discriminator basically thinks that even the fake data created by the generator is real. And it comes to a stage called convergence, where the accuracy of the discriminator is 50%. Basically, it's a coin flip situation, where it's a 50-50 chance that the data that the discriminator got is either real world data or fake data. So at this stage, we have a fairly good generator that can be used for applications. So there are some challenges when it comes to training these GANs. So the first challenge is called vanishing gradients. So this happens if the discriminator is too good. If that is the case, then the gradient that basically the discriminator provides in the form of the generator loss to the generator, it will be too small for the generator to adjust its weight. So it's stuck in a situation where the generator doesn't really make any progress. The second challenge is called mode collapse. So this is when the generator is too good and it constantly over optimizes for a particular discriminator. And when it does this, basically the discriminator says that there is really nothing to change in the generator. So what happens is the generator keeps producing the same output or cycles between a small set of outputs over and over again. So one of the objectives with GANs is to create a wide variety of fake data that can pass off as real. But when it comes to if it comes to this mode collapse situation, then the generator will continuously output the same output or a small set of outputs over and over again. And then we come to a third challenge, which is called failure to converge. In this situation, if the generator keeps training far beyond the point where the discriminator reaches the 50% accuracy, so the convergence point, then at that point, because what the discriminator does is a coin flip, the data that in the form of generator loss that the discriminator provides as basically back propagates to the generator is meaningless, because it's basically it's doing a coin toss to decide if it's a real image or a fake image, or real data or fake data. And so the discriminator doesn't really give any meaningful feedback, and because the generator receives this meaningless feedback, it adjusts its weights based on that meaningless feedback, the accuracy of the generator can start to drop again. It can reach a good point and then it can start to drop again. So that is failure to converge. So these are the main three challenges that AI developers and data scientists should overcome when it comes to training a generative adversarial network. So next we look at a few applications of GANs as well as potential implications of GANs existing in the world. The biggest application when it comes to GANs is the generation of synthetic data, the generation of fake data that is basically indistinguishable from real world data. So this can be images, audio, video, text, or numerical data. So for example, you can see these 6 faces on the right. None of these people actually exist. These are all faces that were basically fake faces that were created by a GAN, and you can see that it's hard to really say, even for a human being to say if this is a real person or a fake person. So data like this is especially helpful when it comes to training other AI models, especially in a situation where now there are more and more stricter restrictions when it comes to privacy. So there are laws like the GDPR and HIPAA where private data cannot be disclosed. If I were to give an example, so for example, if a company that specializes in creating AI solutions for medical purposes, and it trains on real world medical data, they could find themselves in a situation where they can't publish a data set because the data contained is private medical data of patients. So what they can do is, instead of disclosing that data set, they can use that data set to train a GAN, and then that GAN can be used to create fake data, basically synthetic data that is similar to the real world data, and then that data set can be published because it's not real world data, and that data set then can be published as an open source project, can be used by other researchers. So it manages to create data without violating the patient's privacy. So it has immense advantages like that. And then when it comes to there are also applications when it comes to repairing and enhancing images or videos. There are 2 major areas when it comes to this. One is called image inpainting. So basically you take images or videos and you reconstruct missing parts or corrupted parts of that image using GANs. Another area is called super resolution, where you generate a high resolution image or video from lower resolution images and videos, basically upscaling those images and videos. Another very interesting application is called image to image translation. So basically it can create a separate set of data that can belong to a completely different, a similar but different set, based on a data set that belongs to a completely different set. So for example, here we can see that the GAN can take photos of horses and create a data set consisting of images of zebras. So this is a very creative application when it comes to GANs. And moving away from things like images and video, multimedia applications, it can even have, so like I said, you can use numerical data, text data as well. It can have applications even in fields like medicine. So one potential application is called drug discovery. So basically it can take from a drug database already existing drugs, and then it can take drug candidates that have been proposed to cure a certain disease, for example, like we have these days, like the coronavirus, and it can basically use a GAN to discover new drugs that previously didn't exist. Basically the generator samples drug candidates for a given disease, and it can be used to basically discover new drugs that didn't exist before, that can cure previously uncurable diseases. So what are the negative implications of GANs? One of the biggest when it comes to privacy and people's personal rights, one of the biggest implications is the concept of deep fakes. Basically creating fake imagery or videos of persons without their consent. These could be images that are indecent, that basically the real person wouldn't want to be out there, and such images and videos can be created without their consent. For example, a very famous example here is a video of the US President Barack Obama, who seemingly kicks a door in anger when he leaves a press conference. So this was actually promoted a lot among his opposing groups, to show that he can't control his temper. So basically used for a political attack. And as we can see in the video, it's very hard to say if it's fake or not, for the untrained eye. So likewise, it can be used to spread a lot of disinformation, for things like political purposes, and can even be used for things like fabrication of evidence for a crime. So it can basically implicate someone innocent in a crime, by fabrication of evidence. So we really need better techniques, as much as we need to improve GANs to create more realistic data. We also need to improve methods to detect which data is fake and which data is real, because otherwise it can have very negative real world consequences in the future. So to summarize, the concept of GANs, or generative adversarial networks, is basically very recent. It came out in 2014. It's a recently new innovation with a massive amount of potential. Its training is based on even older principles when it comes to game theory. Basically, in this case, a Minimax 2-player game. So it has a diverse range of applications, and if used correctly, it can even be used in applications that can potentially save lives, like the example I gave before when it comes to drug discovery. However, we need to be careful, because in the wrong hands, that technology also has the potential to do a lot of harm. These are the references that I've used when it comes to preparing this presentation. Thank you very much, and I can be reached in the information given here. Thank you very much.